Derivatives of trig functions. You must absolutely have these memorized. Once again, after today, I would hope that you have 6 new flashcards added to your collection when we get done today. Okay, first, the derivative of the sine is the cosine. The derivative of the sine is the cosine. That's the easy one. The derivative of the cosine is the negative sign. It is not the sine, it is the negative sign. I'm telling you, landmine warning, you gotta watch which one's positive, which one's negative. That's what I say, you gotta have to memorize. The derivative of the sine is the cosine, the derivative of the cosine is the negative sign. Okay? So, first 2 rules you gotta have memorized. Okay, using those 2 rules, let's find, and this is a proof of what is the derivative of the tangent. Well, we don't have a rule for the derivative of the tangent. And remember, I told you, we're not going to use limits to find derivatives anymore. So we're not going to do that. What we are going to do is we're going to monkey around with this. So the derivative of the tangent is the derivative of the sine of x over the cosine of x, because isn't the tangent sine over the cosine? Rewrite it. Go from there. Okay. So I have a quotient. I need to use the quotient rule. Okay. So the quotient rule is the derivative of the numerator times the denominator. The derivative of the sine is the cosine. So I have the cosine of x times the cosine of x minus the numerator, sine of x, times the derivative of the cosine of x, the denominator, the derivative of the denominator, which is negative sine x, all over the denominator squared. And cosine squared, we know that that is the cosine of x squared. You have to understand and remember that, you know, that notation. What I have, because you're going to have sines, cosines, you're going to have them in the powers. You're going to have, you know, the tangent, tangent 5x. Well, that's the tangent of x to the 5th power as a group. You got to remember that. Okay, so let's simplify. Cosine x times cosine x is cosine squared x. Sine x times sine x is sine squared x. And a negative times a negative is a positive over the cosine squared x. What's cosine squared plus sine squared? 1, the Pythagorean identity. One of the few identities you will have to remember is the Pythagorean identity. So that's 1 over the cosine squared x. And 1 over the cosine is the secant. So this is equal to the secant squared x. So the derivative of the tangent is the secant squared. That is a proof. This is technically a mathematical proof. I went from one to another, I went from the derivative of the tangent of x, followed all my mathematical rules, did everything properly, and came out with what it's equal to. This is technically a mathematical proof. So, your next 4 rules, because there are 6 trig functions altogether: sine, cosine, tangent, cotangent, secant, and cosecant. Okay, so once again, you have to know these. You have to know them by heart. They're closely related, but they're not exactly the same. You got to watch your negatives and positives. You got to have memorized. If you don't have memorized, you got real problems going on. Okay. So let's do a couple of examples. The first one, y is x cubed sine x. Let's find the derivative. Okay, y prime. I have a first and foremost, and this is something you're going to have to work at recognizing. It's going to get more complicated in the next chapter. But what do I have? First and foremost, I have a product. I have x cubed times sine x. I have to use the product rule. I have two things I'm multiplying here. I have x cubed times sine x. This is not necessarily obvious, but you need to understand and see that I've got two different functions going on here. So I have to apply the product rule. Product rule is derivative of the first term, 3x squared, times the second term, plus the first term, x cubed, times the derivative of the second term, cosine x. Now, a question I will often get from students is, am I done? Do I need to simplify? What do I need to do to this equation? My answer is, what's your next step? If all you're doing is taking the derivative, stop. Don't do anything else. This is good. It's clean. You can't really do anything else to this to make it look any prettier, because that's all you would want to simplify for, is to make it look prettier. You're not going to make it look any prettier. Now, if we were going another step further, let's say we were looking for a tangent line, or we were trying to solve this to find where the zeros are, which we might do something like that, then I would, set it equal to 0. I would factor out x squared, and that would give me 1 0, and then I'd have to figure out where the other zeros are by solving the trig function separately. But I would do that. But if I'm not making another step, all I'm doing is taking the derivative, stop here. Don't go any farther, you'll just make a mess of things. Okay? And you'll learn when you want to go farther and when you don't. Okay? Okay. Your turn, try that one. Okay, so look at the problem, you're doing the derivative, you have to kind of look at the big picture as well as the individual things. Big picture, I have a quotient. It's kind of obvious. You got a fraction, you got to use a quotient rule. Okay, so y prime, derivative of the numerator, which is 1, times the denominator, minus the numerator, times the derivative of the denominator. The derivative of 1 is 0. The derivative of the cosine is negative sine. So the derivative of 1 plus cosine is negative sine x. All over the denominator squared. Okay? And then you try to see if you can simplify things down. I know, because I've seen it. A lot of you wish to reduce right now. You cannot reduce this fraction, can you? No, because 1 plus cosine x and other stuff does not cancel with 1 plus cosine x. So there really isn't, if I recall, there's not a whole lot I can do. 1 plus cosine x plus x sine x all over 1 plus cosine x squared. Yeah, there's not a whole lot you can do to that. You can't really simplify that. There's nothing neat, no neat identities or anything you can toss in there. Question?
Yeah, you can't multiply the x and the sine.
No, because it's a function of x.
Oh.
Okay. This is x, this is the sine of x. It's not x times sine x, because the sine of x is I'm taking the sine of it. The sine is a function of that object. Okay.
Right.
Nope, no, I see it all the time. Okay, your turn. Do this one. Find the second derivative. Okay, so let's go ahead and do this. So f prime. So c, the derivative of the secant is secant tangent?
Yeah.
Okay. That's when I have to pause. It's particularly because it's been a while. Secant tangent. So that's the first derivative. Second derivative, not a big deal. Same rules, but you have to use the quotient rule. Okay? So you have to use the quotient rule. That's the first term. Product rule. First term, second term. So f double prime of x, the derivative of the first term is, once again, secant tangent, secant x, tangent x, times tangent x, plus the derivative of the first one, secant x, times the derivative of the second one, and the derivative of the tangent is the secant squared, right? And then, yeah, this one you want to pretty up a little bit. So you get secant x, tangent squared x, plus secant cubed x. Just to make it look a little pretty. And it does. It's a little cleaner. It's a little prettier. Combine up like terms. That's essentially all we're doing is combining up like terms. Essentially, yeah.
So what if the squared cube itself on x?
It's standard form. That's all. Yeah. And let me go ahead and just notation by convention. I don't know why. It just is. Okay. Jerk. Yes, we have jerks. Actually, the section that talks about this in your book is called A Couple of Jerks. Really, it is. I thought that was funny. Okay. So the jerk is the derivative of the acceleration. In other words, the fourth derivative is jerk. Position, velocity is first derivative, acceleration is third derivative, jerk is the fourth derivative of the position. Okay? Jerk is what makes you motion sick. It's not, it's the change in acceleration. That's what it is. That is one of the things that makes people motion sick is jerk. It's the change in acceleration. It's that sudden change in acceleration. That's what tends to make people sick. Yes. It's the fourth derivative. So S of t is the position. They use S for position. So the first derivative would be what? So velocity is the first, speed and acceleration and jerk with respect to t. So here we go. Let's do this. If S is my position, V of t is S prime of t, the first derivative. So I take the derivative of sine, cosine. So I get cosine t minus sine t. Okay. Now that's velocity. Speed, what's the difference between speed and velocity? Direction. Velocity has direction, speed does not. Speed is the absolute value of the velocity. So just put absolute value of whatever you got over the velocity. That's what speed is. Speed is the absolute value of velocity. Speed has no direction. Your car has a speedometer, does not have a velocity. Okay. Think about it. Okay. And then what do we want next? We want acceleration. So A of t is equal to the derivative of the velocity, which is the second derivative of the position. So the derivative of the velocity, derivative of the cosine, negative sine t, and the derivative of the sine is negative cosine t. The derivative of the sine is cosine, but it's a negative, so it's negative. Okay. And then we get to jerk, or j of t, which is the derivative of the acceleration, which is the second derivative of the velocity, which is the fourth derivative of the position. So jerk would be the derivative of negative sine t is negative cosine t. Derivative of cosine is negative sine, so that would be plus sine t. Sometimes it's that easy, sometimes it's not. Find the smallest and largest position, speed and acceleration, and jerk. Look at the functions above. Yes? It's the fourth derivative of, first A prime. So Sorry, third derivative, no, not fourth. My bad. Third derivative is not fourth.
Is there a fourth?
Oh yeah, you can take the fourth derivative, fifth derivative. You can take as many derivatives as you want. But it doesn't really matter. It's kind of like polynomials. We talk about monomials. We talk about binomials. We talk about trinomials, and then polynomials. Right? Because everything bigger than 3, screw it, we'll just call it that. That's kind of where we're at here. And you don't really, honestly, you don't use jerk a whole lot. Although if I recall, there's a really good homework question. One of the things I like about your textbook is that some of the homework questions really give some good real-world examples of what you're dealing with. And if I remember right, there's one in there about jerk and about car engines and about how you can, why higher revolutions or high RPMs are bad for your car, and you actually use the math and use jerk to examine that. Let's see what that is. Okay, so part B, it says find the smallest and largest position, speed, acceleration, and jerk, and so on. Okay, so here's the thing, and there's a few ways to do this. If I look at the original one, sine t plus cosine t, the largest and smallest possible values, if I add those two together, so I got to look at what's going on with those two functions. Now, the easiest way to do this y equals, and my function list, sine x, is it sine x plus cosine x for the original one?
Yeah.
Oh.
Don't give them the row.
Ah.
Get mad. Get yes.
Okay, so if I look at this graph, what are my largest and smallest possible values? 1.4141. So 1 and it's the power over 4, so that's root 2 over 2. Yeah, so this is where we're looking at for these two functions. This is what I have. What's my largest, what's my smallest? If all I do is take this and put negatives and positives in different places, because if I recall, they're never both negative and positive at the same time. Look what I got going on. My minimum and maximum value is the same for every single one of them, except for speed. What's my minimum speed? 0, because it can't go negative in speed, because it's the absolute value. Okay? So this is one of those things, you know, taking a graph to look at something really can make the difference. Make it easier to analyze what's going on. The other way to do it is make a table of values and figure out what the two of them are and add it together. Use your unit circle. What's going to be the biggest one when you combine it? What's going to be the smallest one when you combine it? Which is kind of a pain, but if you got a unit circle in front of you, actually it's not that hard. Add the two, add the two, add the two, subtract one from the other, subtract one from the other, subtract one from the other. Let's see what you get. Okay?